And in between, please ask. So last time what we discussed was principal component analysis, PCA, a dimensional reduction technique. Okay, Priya says that how to create covariance matrix. Okay, we can talk about that. Any other questions? Okay, so let us see. I will share the same slide again. Let's go back to the yesterday's notes. We're talking about the PCA. So Priyank is asking about how to create covariance matrix. So this is how we do it. We take a pair of feature x1, x2. So the dimension of covariance matrix is n cross n, where n is number of features. So first thing that we need to be clear about is covariance is calculated between every pair of features. Right? So that's why we have n cross n matrix. It can be a diagonal matrix also because values across diagonal are duplicated. It is n cross n matrix. Now the step to create covariance matrix is first of all find out mean of the data. So here in this example, data is two-dimensional. We have two features, x1 and x2. X1 and x2, right? These are the two features for which we want to calculate covariance. So what we do is first we find out mean of x1 and mean of x2. Then we remove mean from the data set. So that mean becomes zero in a way. So this is standard practice to make data set zero mean. So this is after mean removal, x1 minus mu x1 and x2 minus mu x2. And then first let us look at how covariance matrix look like. Covariance matrix is a, as I said, n cross n matrix, where n is number of features. So features are listed in row also and in column also. Right? Are you with me so far, Priyank? Okay. So if I look at this cell, first cell, x1, x1, then what does this value represent? Variance, actually we are calling it covariance. So let's say covariance between x1 and x1. So when we are talking about same feature, it is not covariance, but it is variance. Right? And then if you look at the second element of the first row, then we have covariance between x1 and x2. In our example, it also turns out to be 1, but it can be different also. Right? Now from where does we get this value? So we get this value as per this table. We calculate mu minus x1, mu minus x2, and mu minus x1 square, mu minus x2 square. These two columns, mu minus x1 square and mu minus x2 minus mu x2 square and x1 minus mu x1 square. These two columns will give us variance, which is square of standard deviation. So this is variance, which will go in diagonal of the covariance matrix. And to calculate covariance, we will take x minus mu1 multiplied by x1 minus mu x1 multiplied by x2 minus mu x2. That is called covariance between x1 and x2. It also turns out to be 1 here. And if you see, Covariance is not directional. So x1, x2 covariance is same as x2, x1 covariance. So these two elements, the first row, second element, and second row, first element, are representing same thing, right? I forgot to share the notes last time, but I will share it today, so it will be clear after this. But this is how we prepare covariance matrix. And then things are simple. After covariance, we calculate eigenvalues and find out new principal components. And the components for which eigenvalue is very low can be removed. So in this way, we say we have reduced the number of dimensions. Any questions on this? Okay, so we'll see this in working in our lab this Saturday. So with that, let us move to the next topic. Again, dimensionality reduction and very interesting algorithm. It also has some application of eigenvalues and eigenvectors. Important part here to know is the eigenvalue of n cross n matrix up to 2, 3 you can calculate manually. But when the dimension of covariance matrix increases, like for 4 cross 4 or 10 cross 10, then eigenvalue calculation becomes complicated. Okay, so with that, go back to another interesting dimensionality reduction technique, which is known as latent semantic indexing. And I need to find the note again. So I have done this approach of dimensionality reduction with some purpose. So there are two underlying purposes, and I hope to get it to during the lecture. So one purpose is to give you an idea of underlying mathematical concepts, because even the algorithm changes, the underlying theory and mathematics does not change. So that is why, as a machine learning engineer, it is important to be good in probability and linear algebra. So that's why I have chosen the algorithms which has strong application of this probability and linear algebra. That is one thing. Second thing is, all these algorithms are kind of benchmark in the field of machine learning. They have pushed the field in a certain direction, and it has opened new avenues of applications and a new way of doing things. So in that context also, these are important algorithms. Nowadays, we have much more sophisticated and modern approaches available to do the things, but the ground is set by this kind of algorithms. So that is why it is important to discuss this algorithm. For example, in principal component analysis, I focused on the theory of eigenvalue and eigenvectors and how are they important in field of image processing and machine learning. Now, while we are discussing the second algorithm called latent semantic indexing, we will discuss it with a motivating example, which you can see on your screen. And purpose is that it opens a new field of application for machine learning, which we all are nowadays using. And you know that it is search application, right? So we all do searching these days. So whenever some question is asked, our first instinctive reaction is to look at what Google says. We fire a query in Google, and Google will give us answers. So how does this happen? Whatever query words that we have entered in Google search box, Google will compare those query words with the documents available or the web pages available, and it will find out the most relevant page for us. The most relevant page, it will fetch the most relevant page as an answer, right? So how does that happen? So for that, Google keeps a huge vector of document and words, something like this. Through web crawling is part of information retrieval, where Google do the web crawling and list out all the web pages available online and store it in memory with some index like this. So again, a big matrix, huge matrix of document and words. And when you imagine this matrix as on a web scale, you will realize how complicated it can be. Right? Like how many documents are there on internet? So of course, millions of documents are there, right? It is like counting number of stars in the sky. So this base, there are so many documents on the internet. So D1 to DN are all such documents available on the internet. And W1 to WM is a complete vocabulary of a language. So for example, if our search is restricted only to English, then W1 to WN at the most can be what? What can be size of number of columns in this vector? All the legit words of English, right? So entire dictionary can fit here. And to make things worse, we also use words which are not official. Official. We spell the word differently. We use unofficial words. Right? So that's why the columns in this document on this vector can be still larger. Right? Is the situation clear? What we're talking about? Okay. So a Word document vector is a n cross m vector, and every cell indicates importance of the word in the document. So this value is some random value which I have put here, for example, like this 2.9, 3.4 and all that. So it shows that how important the word is for the document. In its simplest form, it can be the number of times a word occur in the document. So for example, document 1 is about cricket and the word batting occurs 5 times, then I would put 5 here. Document 2 is about politics and batting doesn't occur here, so I will put 0 here and so. So in its simplest form, it can just be a row count of how many times a word occurs in the document. But it can be much more better than that also, because we need to normalize, we need to see how important the word is. So if a document has 100 words and one word occurs only 5 times, then you may want to put 5 by 100. And if some word occurs 6 times in a document of 1000 words, then you will put importance as 6 by 1000 and so on. And then you normalize, put it in a scale and range and all that. But in a simplest form, this shows that to make the thing simple, we can say this shows how important the word is for the document. There are much more sophisticated techniques which we have not talked in our discussion, but I think you might have seen somewhere in lab also, which is called TF-IDF. TF stands for term frequency. That is how frequent the term is in the document. As I said, it's counting how many times a word occurs in the document. And inverse document frequency is how much important the term is for the document. To give you some insight on this, but before that, have you used TF-IDF? Has anyone used TF-IDF anywhere in their experiment? Okay, Bhavik says yes. Okay, good. Others, I'm not sure. Okay, but in this lab, next lab, we will discuss that. We'll see how to use TF-IDF also. So, for example, let me ask you a few intuitive questions to understand what TF-IDF is all about. So, if a word occurs 2 times, word 1, W1, occurs only twice in a document, and word 2 occurs 10 times in a document, then which word is more important for the document? W1 occurs only twice and W2 occurs 10 times. Then which one is more important? Word 2, right? Okay, so this is an intuitive answer. But now if I say that, or if you go a bit deeper into the natural language text, then you would realize that sometimes more frequent words are not useful at all. In a paragraph on cricket, let's again continue the same example. Like if you want to talk about the game of cricket, then articles like a and the would occur more frequently than words like batting, bowling, fielding. Isn't it? Because every sentence needs a verb, auxiliary verb, an article. These are common in all sentences. So just counting frequency would not help. But you also need to see that compared to other documents, if there are two documents D1 and D2, and some word occurs with high frequency in both of them, then that word is not important to distinguish between D1 and D2. Rather, you want to look at words which are frequent in D1 but does not appear in D2, and words which are frequent in D2 but does not appear in D1. You want to look at this kind of words to rank the document. Does this make sense? Right? So you don't want to look at only occurs of word in a document, but you also want to see how frequently the word occurs across the document. So that is why it is not just term frequency, but also inverse document. So that is why it is not just the frequency of word in a document, but you also want to look at across the document how frequent the word is. If a word is frequent in all documents, that is not important. But if a word is frequent in only a specific document, then it is important. So that mix is called CF-IDF. Let's take an example. There is a document one is dog says wow. Document two is cat says meow. And document three is bow bow meow meow. Let's say we have created these three documents and we want to index them. So how do we index? So let us say we are just using row frequency count. So we'll see how frequent the words are in the document. So in document one, dog occurs 1, says occurs 1, bow occurs 1, cat does not occur in document 1, so count is 0, and meow does not occur in document, count is 0. For document 2, dog does not occur, so count is 0, says occurs, so count is 1, right? So document 2 is 01011. That is cat says meow. Document 3 is bow bow meow meow. So 0022. Bow occurs twice and meow occurs twice. The dog, cat, and says does not occur in the document. So this is word document vector. And we have used just row frequency to rate the importance of a word in the document. Now let us say query is cat meow. Somebody wants to search for a document that talks about cat meow. So this is query vector. So which document will be ranked, should be retrieved in first position if the query is cat meow? D2, right? D2 should be retrieved. So how do we do this? Do you know any way to do this? We want to compare the words and see that how many words are contained in each document and find out some measure. But there are some interesting measures available, which I'm not sure if you have studied somewhere else or not, but it is important to discuss here. For example, one is distance measure, second is similarity measure. Have you heard about distance measure and similarity measure? Now all these are vector, right? These documents in Word are vector. So that's why we call Word document vector. You can see that document is in n-dimensional word space, or you can say Word is in n-dimensional vector space, document space. You can make document as axis and find out points corresponding to Word, and you can make Word as an axis and find out documents corresponding to the Word. So now these are vectors. I can create three-dimensional vector like this. If I want to calculate similarity of documents, then I will create vector of words. Also axis, I will make axis as words. So this is dog x. Then this is another face axis. Then another bow axis. Then some cat axis. And then some meow axis. And then every document will become a point in this five-dimensional space. So for example, D1 can be here. I don't know how to show it in five dimensions. But let's say D1 is here. D2 is somewhere here. D3 is somewhere here. And so on. And then our query will also fall somewhere. Query is somewhere here. And then you need to calculate distance between this query, distance of this query from all other documents. And return the one which is nearest. Right? So this is called similarity measure or distance measure. There are two types of measures here. Now can you tell me the method that you can use here? Again, a very popular method which you have learned in mathematics is called, so make query vector like this, 0, 0, 1, 1, and make find a point for query also. And then, again, a very popular measure which is called cosine similarity. I'm sure you all have heard about this, haven't you? Take cosine of query Q with all documents D1, D2, and D3. And return the document with highest cosine similarity as a most relevant document. So cosine of Q1D, Q1D1, cosine of Q1D2, cosine of Q1D3. If you calculate cosine similarity between them, then Q1 will get highest rank, I guess, because it matches most of the points. Dot product, essentially. So most of of the dots are matching for query and D2, and two dots are matching and one is not matching. So only one dot is not matching, four dots are matching. Or 4 points, they are matching 4 points, four dimension, or one dimension is different. So D2 and Q cosine similarity will be maximum. So using cosine similarity, you can rank like D2 as top rank, D3 as second rank, D1 as third rank, because nothing is matching in D1 and 12. Cosine similarity between D1 and Q is 0. Right? Are you with me so far? Any questions? Is this clear? Okay. So this is how the document vectors are constructed, and queries compared with various documents. And one measure I talked about was similarity measure called cosine similarity, which you have studied in mathematics. And I also said distance measure, and you also know distance measures, but I think you might have heard it in mathematics, which you are not able to relate. But one distance measure that I am sure you all know is called Euclidean distance, isn't it? Look at the distance with 2 points. So that is distance measure. We will see some example of distance measure also when we talk about clustering. So this is the setup, and of course this is very, as I said, very basic example. Nowadays the search has become much more sophisticated than this. But the problem that we want to address here or discuss here is, as you can see, the number of columns is the size of vocabulary of a language. So English, if you talk about English language, then English language can have around 10 million or maybe around a million words. So that is a million of or 100 or 400,000 words as dimension. This is a very huge vector. And the problem here is, when the vector is so huge, not all document uses all word of the language. Right? So most of the words will get the value 0. Like if the document one has only 3 words, cat says me, and you are creating a dimension of entire vocabulary of English, then most of the data will be 0. So there is problem of sparse data. Only a few of them will be 1 and everything else would be 0. So when you calculate cosine similarity, the 0 value will dominate, and the differentiating values are very less. So that's why you will not be able to differentiate between query and document. Right? So there is a problem of dimension. There are so many words in a language, and that makes a huge number of dimensions for every document. And then with such a huge dimension, storage is also a problem, that you cannot store such a huge vector. And when the scale changes, the entire complexity of the problem changes. That we have seen through algorithm also. When you are working on large data, you need to come up with novel techniques to deal with them. So important part here is to reduce the number of dimensions. That is the theme of the few lectures that we are going to discuss about. So how to reduce dimension here? That is the question. So we have a Word document vector, and we want to reduce dimension of this vector. One approach that we can take is PCA, where you create again the covariance matrix and calculate the dimension. But with such a huge number of words, it is very difficult to create large covariance matrix also. And on such a large covariance matrix, even PCA is also not very efficient. Because eigenvalues, as I said, to find eigenvalues beyond So matrix of size 4 or 5 is very complicated. So what we do then? So that is why we talk about this latent semantic indexing technique. Idea is that we want to reduce dimensions of word document vectors. So number of documents and vector words are very high. Without reducing dimension, most of the features, dimension word count per document will be zero at this stage. So that will be sparse data. So our first goal is to reduce dimension to avoid sparsity. Second is we want to relate word and document. If we can directly compare document with document and word with word, then we have two separate interpretations. Like we can relate words also, we can relate documents also, and dealing with this large dimension will also not be necessary. So, for example, why we want to relate word and document. So, document one is say bank, money bank. I'm talking about money bank, and document two is financial institute, or document two is river bank. In both the words, word bank is used, but the sense of the word bank is different. In first case, the sense of the word bank is financial institute. In second document, sense of the word bank is river bank, right? So now if a user search for the word bank, then both documents will come up with equal number of, both documents will get equal rank. But we need to know that which bank the user wants to search for, whether it is financial bank or it is a river bank. That we need to figure out. Similarly, if you are talking about movie review system, then in one review you see the word good movie. In second you see the word nice movie. Then we need to know that good and nice are not actually two different dimensions. They are same. They want to convey same thing. Right? So this is in linguistic features, this is called polysemy and synonymy. The word bank is polysemous. It means two different things, river bank and financial institute. On the contrary, good and nice are synonyms. They mean two things. So word as a dimension is not a very good idea. Right? So one problem is because of the vocabulary size of a language, you have thousands of words, so thousands of dimensions. That is one thing. And even if you do this, somehow you manage the storage capacity and processing power and come up with algorithm. Still, the problem is not solved because words can be synonym, words can be polysemous. So even if you make word as a dimension, your system won't be precise because bank can mean more than one thing. Good and nice can mean more than one thing. Actually, even in our trivial example that we discussed above, that dog and cat, right? We just use few words. Dog says pow and cat says meow. Do you know how many senses a word dog has in English dictionary? Dog can be a noun, dog can be a verb. As a noun, dog can be a four-legged domestic animal that we all know, or most of the time we use the word dog for. Second is dog is a very detestable person also. We call someone dog if we don't like that person. So that is also a sense of word dog. I dog you to pay attention in class. So there is a use of dog as a verb. So in this sense, dog becomes verb also. So yes, so there are so many senses of every word. So one word as a dimension is not a good idea. So that's why we need to mix up this entire word and document space and come up with something more semantically important or more semantically relevant to get the actual sense of the document. When I want to find out sense of word bank, I need to look at the nearby word, whether it is money bank or whether it is a river bank. Only then I will be able to make sense of word bank. So that's why I want word vector and document vector. Yeah. So this was the setup. And how do we do this? So for that, the technique is called latent semantic indexing. It is based on again a very important linear algebra principle called singular value decomposition. Have you heard of this before? Singular value decomposition? Okay. Okay, then we'll take some examples here so that it will be clear. So singular value decomposition theory says that you can take any n cross n dimensional matrix and you can divide it into three matrices. Use sigma v transpose, and when u and v are orthogonal matrices, and sigma is a diagonal matrix. Only diagonal elements are there. So that is theory of singular value decomposition. How does it fit in our story? It fits in our story because we are dealing with m cross n dimension matrix, where n is document direction, a dimension, and m is word dimension. And we want to break it down into document matrix and word matrix. So in our context, we use this singular value decomposition technique to decompose the word document matrix into three matrices. Use sigma and v transpose, where u is a document matrix and v is word matrix. So C becomes an n cross n word document vector, where n is number of documents, n is number of words. U will become m cross r matrix, where r is rank of the matrix, which is a document vector. Vt is r cross m vector, which is word cross word, and sigma is a r cross r diagonal matrix, which again contains our superhero eigenvalues, but it is square root of eigenvalue, which we call singular values here. So any m cross n matrix can be broken down into this three: m cross r cross m, and diagonal matrix. Let us take an example for this. So if you have not studied singular value decomposition, then I believe that you might have heard about diagonalization of a matrix. A matrix D can be diagonalized as S, A, N, S inverse. But here D is n cross n matrix. The same idea is used in singular value decomposition for m cross n matrix. Let us see one example. So let us say C is a 5, 5, minus 1, 7 matrix. And we want to find out its singular value decomposition in form of U sigma and V transpose. So first we do C transpose C. So C transpose C will be a bit of mathematics here. V sigma transpose U transpose into U sigma V transpose, which becomes V sigma transpose sigma V transpose, right? And from that we can say that, and this is, let's call this equation number 1. And second equation we achieve by shifting V transpose on this side. So CV is equal to U sigma. That is second equation. So first thing is finding how to find this C transpose C. So let's try to find out this C transpose C. So C is 7. So C transpose is 5 minus 1, 5, 7. And if you take C transpose, it will be this thing, 26, 18, 18, 74. Then find out eigenvalues and eigenvectors of C transpose C, because that will give us our sigma. So lambda 1 is 20 here, lambda 2 is 80. These are eigenvalues. And corresponding normalized eigenvectors are minus 3 by root 10, 1 by root 10, V2 is 1 by root 10 and 3 by root 10. And from that, using the define V and sigma, because we said that, let's see how we define V and sigma. So sigma is square root of eigenvalue, that is diagonal matrix. So eigenvalues are 20 and 80. So sigma will become 2 root 5, 0, 0, 4 root 5. And V will be the corresponding eigenvectors. So that is minus 3 root 10, 1 root 10, 1 root 10 and 3 root 10. So that will give us sigma and V. And second question is how to find out U. So same thing, again do C. First you did C transpose C. Here, you did C transpose C and find out eigenvalues and eigenvector to find out V and sigma. Now you do C transpose and you will get the equation of U sigma U transpose. That is again diagonalization, where sigma is eigenvalues and U is eigenvectors. You will get again the same eigenvalues 20 and 80, and vectors will be now 1 by root 2 minus 1 by root 2. I am not repeating the computation because I want to move a bit faster, but if required, we can spend some time on this mathematics also. So this will be the eigenvectors which will define U. So at the end, what you get for this matrix 5, 5 minus 1, 7 is a matrix U, which is a document matrix, sigma, which is rank matrix of eigenvalues, and V is word matrix. And now how do we reduce dimensions here? We reduce dimensions by removing the diagonal. So by arranging diagonal element in descending, the value with highest eigenvalue will be first and so on, and then remove the diagonal value which are very low. Remove that and you achieve dimensionality reduction. So this is how it works. So we are given a word document matrix A, which we divide into three matrices, U, sigma, V transpose, where U is document matrix, sigma is singular values which are square root of eigenvalues, and V transpose is word matrix. And what we do is we ignore low singular values. So in this singular value, arrange diagonal in descending order of eigenvalues and remove the values which are low at the end. So you take only first R singular values which are non-zero, then you get only important factors here. Right, so this is latent semantic indexing. So two interesting algorithms we had finished here. I would stop here, and Saturday we will see principal component analysis in working. We will also try to see if we can schedule for latent semantic indexing in the same lab so that you can see it working. Another thing I want to add here is, of course, I forgot to share notes last time. This time I will share notes today itself so that you can start referring to that. And also understand the two things that you need to keep in mind. One is understand the underlying mathematics, and second is understand the applications which are solved by this kind of interesting mathematical ideas. So these are the two things to take home after this talk. And just make sure that whether you got these two technique correctly or not, I will end with one question. I will not answer it here. I would like to hear it from you. So after the applying PCA or singular value decomposition or latent semantic indexing, the dimensions that we are getting is a subset of original dimension or a set of new dimensions which are lesser than the original dimension. What is your answer on this? So the axis or the dimensions that we are getting after PCA or SPD are subset of the original dimensions on which data was defined, or it is completely a new set of axes on which we are defining the data. What is your answer for this? PL says new. Yes, PL. So it will be a completely new set of dimension. It won't be subset. So we are not removing some dimension, but we are projecting the entire data set on new set of axes and then we remove some axes. So we will come up with a new set of dimension. And that is why the name of this technique is called latent semantic. The Word document vector that we had started with was not latent, it was visible. The document has certain number of words and every word was explicit. So it was explicit. Now what we have found is something latent. So we have got a new set of dimensions from that word dimension. We don't know whether it corresponds to a specific word or not, but this is a new latent index. So that is why the name of this technique is latent semantic analysis or latent semantic indexing, because now the dimensions are not directly visible from the document. These are new set of dimensions that we have created by looking at all words and all documents. And our hope is that it will reveal the underlying semantics. Like as I said, the bank is polysemous, good and nice are synonyms. So it will try to capture those synonymy and polysemy and create new axis or new dimension. So that's why the name is latent semantic indexing. So I will stop with that. We will meet again on Saturday, and during lab we will talk about this technique in more detail. Thanks.